Today we're going to be talking about how to write a logistic growth equation and find a given population after a certain time t, given that we have a value for an initial population, carrying capacity, and at least one value for population after a specific amount of time. So in this particular problem, we've been told that our initial population is 1,000, that carrying capacity is 10,000, and not that we need to know it for this problem, but carrying capacity is just the amount of population or the number in the population that can be supported by the environment before the population starts to reduce because it's overpopulated. So carrying capacity is 10,000, and then we've also been told that the population after 1 year is 2,500. We've been asked to use this information to write a logistic growth equation that models it, and then find the population after 4 years. So what we need to know are the formulas that I've written here. The formula for dp over dt gives us an equation for how population changes over time. And so we will plug our values into this equation, but then to find a value for p of t that models the population over time, not the rate of change of the population over time, we'd have to integrate both sides of this equation, which we could do, and we'd come up with this formula here, but it's helpful just to know this formula because it's a little complicated to perform the integration on dp over dt. So in order to find our logistic growth equation, we want to write our equation for p of t. So what we'll get here is p of t, and this means the population at time t, is equal to m. M in this equation represents carrying capacity, and our carrying capacity is 10,000. So we'll do 10,000 like this, divided by, in our case, 1 plus, and here we have m again, so 10,000 minus p, and p in this equation is initial population. So we'll take p as 1,000, we'll get minus 1,000, all divided by 1,000, p again. And then we have e to the negative kt. Negative k is a constant that we'll need to solve for, so we'll leave that as it is, and then we'll leave t as it is here as well. Now if we simplify this, we get 10,000 in our numerator still, and then in our denominator we get 1 plus 10,000 minus 1,000 is 9,000. 9,000 divided by 1,000 is just 9, so we get 1 plus 9 e to the negative kt. Now this would be our model for p of t, but we've still got two values in here that are unsolved for, k and t. T is our variable. We still need to find a value for k. The way that we'll do that is by using the information that we've been given that our population is equal to 2,500 after 1 year. So what we'll do is we'll set this equal to 2,500, and we'll call t 1, and that'll leave us just with k, and we'll be able to solve for k. So we'll get 2,500 equals 10,000 divided by 1 plus 9 e to the negative k. T is 1, so we just end up with negative k here in our exponent. Now if we multiply both sides by our denominator here, 1 plus 9 e to the negative k, and then we divide both sides by 2,500, we'll end up with 1 plus 9 e to the negative k over here on the left-hand side, and over here on the right we'll get 10,000 over 2,500, which is equal to 4. If we subtract 1 from both sides, we get 9 e to the negative k is equal to 3. Dividing both sides by 9, we get e to the negative k is equal to 1/3. Then if we take the natural log of both sides, we'll get natural log of e to the negative k is equal to natural log of 1/3. The natural log and the e on the left-hand side will cancel, and we'll just be left with negative k is equal to natural log of 1/3. Multiplying both sides by negative 1 to solve for k, we get k equals negative natural log to the 1/3. Keep in mind here that we can still do some simplification with this. We can say that k is equal to negative natural log times 3 to the negative 1, right? This is 1 divided by 3 to the first power. 3 to the 1 is 3 here in the denominator. If we move that to the numerator, we can change the sign on the exponent to be negative instead of positive. That gets it into the numerator, and we're left with 3 to the negative 1. Now, if we have a constant coefficient on a natural log, one of the laws of logarithms is that we can take this constant coefficient, in our case negative 1, and raise whatever's inside our natural log here to that constant coefficient. So what we get here is k equals natural log of 3 to the negative 1 raised to the negative 1. And when we have an exponent raised to an exponent, we just multiply them together and we get here a positive one. So what we see here is that our value for k is going to be equal to natural log of 3 because negative 1 times negative 1 is a positive one. Now, if we plug that back into our equation here for P of t, what we get is an equation for P of t that's only in terms of t. So P of t is equal to 10,000 in the numerator divided by 1 plus 9e. Now here's where our k comes in. So we have negative natural log of 3 times t. And that'll be our final answer for P of t. That's our logistic growth equation. Now we need to use that to find population after 4 years. And all we have to do to find population after 4 years is plug in 4 for t. Remember, t represents time, so we just plug in 4 for t, and we get 10,000 divided by 1 plus 9e to the negative natural log of 3 times 4, so times 4 here. And what we get here, if we do this math on our calculator, is a value for P of 4 of 9,000. It works out to be 9,000 exactly. So we know that our population after 4 years will be 9,000, which is just 1,000 short of the carrying capacity. And that tells us that soon after 4 years, we're going to reach the carrying capacity for this population in this environment. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.